Okay, good afternoon. So last time, we went through other ways in which ammonia was being produced, and then we said how Ramsay and Young did a very simple experiment where they heated up ammonia in presence of a iron catalyst, and they found that it decomposes to nitrogen and hydrogen, but always there was a residual smell of ammonia, and which, as one of you suggested, was indicative of an equilibrium. So, that was the kind of one little clue that someone needs to latch on to. I'm not sure who it was, whether it was Haber or Nernst or Le Chatelier, but they were all active in this area. All these great names that you are familiar with, and also Ostwald also. I read in some biography that Nernst had actually advised someone to ask Haber to do some experiments varying the temperature and pressure. Maybe the idea came from Nernst or it originated from Haber itself, but it's not so important. What is important is that there was a feeling that there is an equilibrium control to this reaction. At that time, Haber was extremely fortunate that he was able to carry out these reactions, and only Haber could. Le Chatelier and Nernst, I believe, were not able to, even though they might have been intellectually ahead, but they were not in a position to carry out these reactions, which Haber did. Haber actually generated this very important data, and this I've taken from his Nobel lecture. And what he was able to show was that he was, I think, able to explain why Ramsay and Young were why the whole thing around 1000 degree was decomposing to nitrogen and hydrogen, but why there was a faint smell. So when Haber did an experiment, say at 1000 degree centigrade, I think probably trying to use the same catalyst that Ramsay and Young had developed initially, and also kept it around what atmosphere. That was the typical condition under which Ramsay and Young had done their experiment. So what he found is that there is an extremely low conversion of nitrogen and hydrogen to ammonia. That's all it was, 0.0044%. But that is sufficient to get a smell of ammonia. So I think the two results were consistent. I'm not very sure whether Haber had always studied the forward reaction, or whether, like Ramsay and Young, he generated this data by actually taking ammonia and then studying it at different temperatures and pressure. It doesn't matter which way he approached the equilibrium. What he was able to undoubtedly show was that as he reduces the temperature to something like 200 degrees centigrade, and as he increases the pressure to around 100 atmosphere, that you can get as much as 86% conversion. The reason it looks like, it was in the reverse direction, because that there was no catalytic process that was known at that kind of a low temperature. Another possibility is that he just left his reactor running for days together, and after that he measured the equilibrium. That's possible. But so he was able to show that in principle it's possible to actually get a very high conversion. But as we all know, Ramsay and Young had not found any catalytic activity of the iron catalyst, whatever he was using, at any low temperature. So he was studying it at something like 1000 to 1200 degree centigrade temperature. Haber established this, but there is something very interesting which I should point out, that what do you think was special about Haber, which enabled him to do these studies? Why is it that Nernst and Le Chatelier could not do it, or Ostwald, but Haber succeeded? What is it that he had? Was it smarter idea or was it something else? Well, it's very interesting. What it is that we have read about the liquefaction of air. So Linde had already been able to generate pressurized air to a pressure of something like 100 to 200 bar. That was possible to do. Okay, and so that was interesting. But what Linde had done was just really dealt with air, not with a chemical reaction. But certainly he had a high pressure equipment. So, and they're all Germans. Linde was a German. Haber was there. Haber would have possibly contacted Linde and said that, would you mind sharing your equipment with me? I'm trying to do some reactions at high pressure and high temperature. Of course, Linde did not use high temperature, but I'm sure that he may not have had to start from scratch. Haber actually showed remarkable tenacity in developing a high pressure equipment, without which it would not have been possible to do these reactions. And Ramsay and Young, frankly, could have done it much earlier, but they probably didn't have that equipment. So I believe the greatest thing that Haber did was really come up with an equipment, because that was at the heart of the whole thing. And so he had the equipment, and that's how he was able to carry out temperatures. You can imagine from up to 1,000 degrees centigrade and 200 bar pressure. I mean, it was phenomenal. This is the first time ever that a high pressure reaction had been carried out, and that too at high temperature. Nobody else had done that. And subsequently, of course, people worked out, I'm not sure who worked it out, but they worked out the enthalpy and the free energy. Presumably, they worked out the equilibrium constant, and from that they got the free energy value. But what Haber then did was that he said that, look, 1,000 degree, so you can forget about it. Even at 200 bar pressure, you will not get even 1% conversion. So unless we can find a catalyst which can operate at a lower temperature, that it's not going to work. So I might have generated the knowledge, but I don't know how to do it practically. And that was very clear that the temperature needs to go down. And they took practical view that if you look at a temperature of, say, 500 degrees centigrade, that's also not bad. He probably already was able to get to temperatures of 500 degree and 200 bar pressure. So he would have said that, not bad. I might be able to get about 17.5% of ammonia, which is not bad. Up to that point, people didn't even know what is the free energy, what is enthalpy, nothing of this reaction. He then switched his attention from data generation to the search for a catalyst, better catalyst. Now, when you are encountering this kind of a problem, that there is a catalyst to be made, okay? And iron was the only catalyst that had been worked on till that time, and that too for the back reaction, really for the decomposition. Where would you begin your search? What would you do if you had this kind of a problem?
So we might look at iron first and then check similar elements.
Great, you have given the answer. But I just want to know from you what is your concept of a similar element.
So iron is 26th in the periodic table, so neighboring transition elements.
This is great.
So same charge to mass ratio in the iron.
Same charge to mass ratio. Students look for elements similar to Fe, okay, as a likely starting point to find a new catalyst. Right? That's what you're trying to say. And look at adjoining elements, right? I think that's what you are more or less trying to say. And then you said look for things with similar mass to charge ratio. That's what you said,
Yes,
right?
Sir.
Yeah. Okay. I must commend you all. Maybe your answer could have been a bit sharper. Now, what have we learned about the periodic table? What kind of elements are similar in a periodic table?
Iron, cobalt, nickel, 3 elements are quite similar in properties.
Iron, cobalt, nickel. Okay. Okay. They're all transition elements for sure. No, but I'm just saying, like when we say alkali metals or alkaline earth metals, what are we talking about? Which fall into a
Single group.
Yes. Okay. I mean, these are all group properties, right? So you actually should look for things within the group, right or not?
Yes,
Yes,
sir.
sir.
But I don't know. But I think this is what Haber did. He would have looked at the periodic table and he would have said, oh, why don't I look at this group over here? I've got iron. He's very, very lucky that he was able to find osmium as a great catalyst. Somewhere in the vicinity of 1000 to 1200 degrees centigrade, there was some indication that iron may be a catalyst, but the same thing osmium could do at a temperature of 500 degrees centigrade. Much later, around I think in the 70s, there was work done in Japan where actually they were able to make an excellent catalyst made from ruthenium. So it's wonderful that looking at the periodic table gave them inspiration. The other catalyst that Haber was able to identify was uranium. I mean, of all things, there had been no study ever on the use of uranium as a catalyst. Uranium around that time had suddenly come into the limelight, as we know, because of the discovery of radioactivity, which happened around the time that Haber got interested in working on ammonia. I don't know why Haber took uranium. Osmium is a bit easier to understand. Maybe because it was gaining in popularity, and he would have said, "Hey, let me try my luck with uranium." So he did that, and both uranium and osmium worked very well as catalysts. That was actually revolutionary. That he was able to perform this reaction at a temperature of, I think, around 500 to 600 degrees centigrade, maybe around closer to 500, and managed to get around 17, 18% conversion. the greatness of Ramsay and Young, the experiment with ammonia, was that it's a thermodynamically favored reaction, and you can in principle carry it out even at low temperature if you can find the catalyst.
So I wanted to
Yeah,
ask that. So can we use uranium as a heating agent, like as the pilot burner, by causing a controlled reaction, like a bomb, sir,
very interesting.
to reach 500 degrees Celsius?
Well, for that you'll require radioactive uranium, okay,
Yes, sir.
because
Yes, sir.
the bulk of the uranium U-238 is non-fissile. You need uranium-235. Not in this course, but in another course that I teach on innovation. Along the lines of what you are saying, I suggested that radioactive elements may be a potentially exciting catalyst, especially to induce reactions by radical pathway. I think that's what you are trying to say. But my feeling is that the uranium, which was catalytically active, was catalytically active because of its chemical properties, not because of its radiochemical properties. All
Okay,
right.
sir. Thank you,
But
sir.
so what happened was that at that point, he had some results, and I think even before that, BASF had gone to Haber, most probably to work on the oxidation of nitrogen to nitric acid. Haber then got BASF interested in his work, and he would have shared the results that he had generated. And based on the results that Haber generated in his laboratory, BASF got interested. And when I say BASF, the person who was leading the show for BASF was Bosch. He was the chief engineer there, and he studied Haber's process and said, this is great what you have done, but this is all of academic interest, not going to be of great interest to BASF. And I'm sure that would have demotivated Haber. Haber would have asked, what is the problem? And Bosch, we learned from his Nobel lecture later on, which he got in the 30s, that that the total amount of osmium that was available in the world amounted to only a few hundred kilograms. And in fact, BASF went and bought all the osmium that they could find. But they said this is not sustainable. You're not going to be able to go into production with such a pittance of osmium. And uranium was not something that they were interested in. I think uranium did not work as well as osmium did. And plus, uranium was too esoteric at that point. So I think that probably BASF were not that interested in uranium. And also uranium itself, its availability at that time was not so well known. So the focus was on osmium. But then what BASF said is that, look, I mean, we will have to go back to the drawing board and find a new catalyst. Where would you look again? What would you look at? You gave such a beautiful answer for the first one. So give me an answer for this also. Where would BASF go looking?
Iron.
Unbelievable. Brilliant. This is really interesting, and it shows you the direction in which your thought should be oriented. Because iron was, after all, the only thing other than osmium and uranium which were known. It was known that it has some catalytic activity. And I have a feeling there was another reason for them wanting to do it. You see, by that time, BASF had already become world-renowned for their contact process, which you have studied. And, in the contact process, what happens is that vanadium pentoxide is, of course, the key catalyst. BASF were greatly able to improve the catalytic performance of vanadium pentoxide by doing all kinds of studies. So they knew how to improve the catalyst. The second thing is that what was also realized by them is that iron is, although we say Fe, Fe actually has different crystallographic forms. Yeah? And so some smart guy might have said maybe it is worth looking at the crystallographic forms of Fe, and see if one is more reactive than the other, and if any of you were to take my future course, the details of that, but iron was a good starting point, and I really am so happy, that you have given this answer. Okay, so I'll just put it down over here. Or maybe not here. I'll put it down. Okay. Now, there's another thing. What do you think Haber would have used as source of hydrogen and nitrogen?
From the liquefaction of air, Linde's
Brilliant.
process, he could have gotten nitrogen.
Wonderful.
And he could have undergone catalytic conversion or catalytic cracking of hydrocarbons to get the hydrogen also.
You are absolutely brilliant. At the end, we'll come to that. Anything else, perhaps?
So the separation of water for hydrogen.
Separation of water means you mean electrolysis.
Yes, electrolysis of water for hydrogen as a source of hydrogen.
Yes, electrolysis of water to produce hydrogen. Now, this is wonderful. I think that this is what Haber used in his studies. He must have got nitrogen from his friend Linde, besides getting some equipment, and electrolysis was something which was already known by that time. People had done electrolysis of water, and people knew how to generate hydrogen. So it wouldn't surprise me if he got hydrogen that way, or it could have been some other ingenious process, Now, but the thing is, when BASF saw this, whatever Haber had used, BASF said, this is not going to be technology. Yeah, I cannot take nitrogen through liquefaction of air, because in those days, it must have been a very costly process. And electrolysis also was a very costly process. Even today it is. So Bosch said, where are you going to get your feedstock? We are not going to be able to get work with this. And so what Bosch did, again, he put another team just to look at what could be the best source of hydrogen and nitrogen. So one team got working on the catalyst, another team got working on the feedstock, and the third thing, which I will not go into here, but maybe at some point you can find out. The third thing, which Haber never says, but Bosch found out, was every second day Haber's high pressure equipment would explode. And so he said, how are we going to do anything with this particular equipment? And so he put another team to work on how to make a better equipment. So that's how basically BASF got going. But had it not been BASF's interest in Haber's work, this would have never materialized. Haber on his own, would not have been able to do anything. As I told you, the Birkelandite process was going great places. People adored that process. So everybody wanted to go by the Birkelandite route. And this was something completely new, esoteric, catalyst not known, feedstock not known. So there was very, very limited interest in this thing. So, but I am so glad, that you have mentioned this.
So can we use producer gas?
Yes. Yeah. Yeah. Producer gas is another way of doing this, which you will get from your pyrolysis processes. Of course, there will be a separation required in all of this. Yes, but you can use producer gas. Certainly.
Thank you, sir.
Anything that gives you hydrogen, you could consider. But BASF, you see, were already very strong in the area of coal. They were already working on coal liquefaction. Even natural gas was something that BASF was quite familiar with. Understand one thing, that today, all the people who talk about steam reforming, this, that, primary reforming, I mean, these were not known. They were invented for the ammonia process. And then, of course, it had much wider applicability in n number of areas. But the basic invention happened only to find hydrogen for ammonia. So, they started working, and they were able to generate hydrogen from coal and methane. They said then, okay, we've got hydrogen. Now, what do we do about nitrogen? We'll have to find nitrogen also. So what would you do for nitrogen? Cheap source?
Sir,
Yeah.
we can, whatever coal or methane we are using, we can partially combust it with the air
Yeah.
that we are using. So that will use up the oxygen and it will
Yeah.
not use up the nitrogen.
Oh my
And then,
God, this is unreal. Brilliant, brilliant.
sir, then by steam reforming of CO, we can also get hydrogen
Hydrogen.
also. So, and then we'll have to
Yes.
separate CO2 and methane from it.
Oh, wonderful. Wonderful. Did you know the answer, or were you guessing?
So I know the answer from before.
Okay. Okay. Because, I mean, of course, I know that all of you are very smart. I know that I would not have thought of it. I can tell you that much. In other words, what you're saying is air as a source of nitrogen, right? And
Yes, sir.
coal as a source of hydrogen. That's what you're saying. And look, today, let me tell you, you can think about these things because we are a bit more familiar. But imagine when nothing like this existed. There was nothing, there was no such thing as steam reforming. And so somebody had to create these. So exactly as you said, and I think that one of the sparks for the subsequent thing was, you see, there was already a concept there, and when in fact Lavoisier had found the life-giving properties of oxygen, and then someone combusted air with some fuel, and they found that I can't breathe anymore, which means that the oxygen probably had gone, that whatever they thought it was, and they called it burnt air. So air had burnt. Not the fuel was burned, the air was burned, and the oxygen was got rid of. Okay, so that's the concept that BASF worked on, and so let us go through it. What and also because natural gas had H2S, so they had to also develop the process to get rid of the H2S from natural gas. So that they could do by treating it with zinc oxide, it forms zinc sulfide. They did a desulfurization. They introduced this chemistry that today we know as primary reforming or steam reforming, where they took methane. And look, this reaction will never happen without a catalyst. And so they had to invent also a catalyst to carry it out. The people didn't even know what is the thermodynamics of this process. Nothing was known. They found a nickel catalyst which could do the job. Then they were able to effectively generate hydrogen, and they also tried to maximize the amount of hydrogen by effectively converting CO as completely as possible. So that's what they did, and they generated hydrogen. And then what they did, exactly as you said, they were able to carry out this process of air reforming. The air reforming process that they did was effectively by exactly as one of you said, was by burning methane with oxygen, but it was not a combustion. It was more like a pyrolysis. So you are, in a way, it's like producer gas. So you are generating hydrogen. This is the chemistry that they developed, and they were able to more or less, consume all the oxygen in the air, and they were able to, if anything, were able to generate more hydrogen from the process. So they got a large amount of hydrogen from the secondary reforming process, and in addition, they had introduced nitrogen from the air. So was now there, nitrogen was there, and so then what they did was they found that there is some amount of carbon monoxide which is still present. So they carried out a water gas shift reaction, and it's done in two stages. There is a low temperature and a high temperature water gas shift. And when they did this, they ended up with carbon dioxide, which came from all of these steps. Most of the carbon monoxide had disappeared when they did the water gas shift reaction. These are the catalysts which they used. And then, once they had, by the way, this is the high temperature shift. HTS stands for high temperature shift, and LTS stands for low temperature shift. And these are the catalysts that are used. Okay. And then, effectively what they ended up with was hydrogen, nitrogen, and carbon dioxide and water, because some water was formed. Then what they did was they had to get rid of the water. So they cooled down, the gas to below the dew point of water. And so they could condense most of the water out. So the water went out. And then they had their brilliant idea of finding a technology for removing carbon dioxide. So today, in fact, all this whole world is talking about carbon capture. And this carbon capture, of course, there are various approaches, but the chemical way to look at it, which people are looking at, is really to use some basic solvent, something like maybe ethanolamine, or an amine, some amines. Okay. And because carbon dioxide is acidic, the amine is basic, so they interact, and also the interaction is not too strong. It's a weak interaction. So you can also heat it up and decompose this salt, and you can again regenerate carbon dioxide and recycle your ammonia, okay, or amine. So what they did was they effectively again discovered this process of separating out carbon dioxide from this. Now, even that, Okay, what they found is that, doesn't matter how good all these processes were, there was always some trace amount of CO and CO2 which was present. As much as they tried, they could not actually remove that CO and CO2 from this mass. So what they at that time thought is that, when they were doing this whole process, and they started with methane, and H2S was removed, etc. You see, they found that some amount of methane also remains, along with their nitrogen and hydrogen which had formed. But when they did the reaction with Haber's process, they found that the methane is not really causing too much of a problem. So that was there. They did not find that. What they did was they now converted these traces of CO and CO2 back to methane. They said this is the best solution to the problem. It's important because you see, when they were working with osmium or iron, you know that you can, and if you have even traces of oxygen, for example, you know that osmium tetroxide is a gas. It can volatilize. Okay, and many of these carbonyls can be volatile. So there would be a serious effect on the catalyst. If these were present, and they might also poison the catalyst. The brilliant thing later on we'll see is that they did not just remove the CO2. They were visionary. At some point, somebody would have said, I am going to convert that CO2 into urea. And look how smart it was. They didn't even know how to do it. But somebody would have said, hey, why don't we take ammonia and carbon dioxide and try to make urea? So this is the difference between engineers and scientists who are in the discovery mode. They are actually discovering things as they are going along in trying to solve a problem. Most of us basically try to work on problems which have already been solved. We do not actually like totally unsolved problems. We might work on variants of a theme. Something is known, I'll do a tweaking here and there, and do some change. But something drastically different, which doesn't exist, it's not there anywhere. Those are not the kinds of things that we are very, very confident about. We're not very happy about working on such things. You all are smart enough, let me tell you, that you should actually be in that discovery mode. So just to show you, so this is the feed gas that they started with, which was mainly methane. Okay, after the sulfur had been removed, the H2S, through hydrodesulfurization. Then in the step 1 of steam reforming, so they ended up converting most of the methane into hydrogen and carbon dioxide. But there was also some amount of carbon monoxide, as you will see. That's bound to happen. Under a reducing environment where you have got methane, it's almost impossible to get full CO2. You can't. Then in step 2, which was the air reforming, so they had introduced air. So that's where the nitrogen came from. Because nitrogen now had quite a bit of concentration, that's also the reason why proportionately the hydrogen concentration has come down. More carbon monoxide was formed in the aeroforming process. You can also see that the excess methane that they took, they were able to reduce the methane to just about 0.7%, starting from 83.4%. Then in the step 3, which was really the water gas reaction, where what they did was they again boosted up the hydrogen And now you can see that most of the carbon monoxide is gone. It becomes just 0.1% because it got converted into CO2. Then what they did was they removed the CO2 with the help of the amine solvent. Okay, so it's gone now, and they also got rid of the CO by the reduction to methane. And look at this, they ended up with a 3:1 composition. And this is the ideal, 1:3. Okay, and this is what they ended up. Now, this is sensational because this is so different from what Haber had possibly worked on, which was pure nitrogen and pure hydrogen from a completely different source. That the moment this was done and a new catalyst had been invented by BASF, the rest of the Haber process became trivial. And in fact, it became a reality. Any questions from anyone? All clear?
So,
Yes.
I have a doubt.
Yeah.
Because this process was not known for the nitrogen and hydrogen, so could they use azides or heating azides as a source of nitrogen then?
Yeah, actually, this is a very good suggestion that you have made. Although I'm telling you that it was from liquefaction of air, I'm not actually so sure. Maybe you're right. There could have been a decomposition of some organic azide, which actually, or even sodium azide, which may have led to the formation of nitrogen. It's brilliant thinking. Let me put it down. So I'm just saying um, air, or maybe from decomposition of azide. I don't know the answer. I'm not sure, but it's certainly a good idea.
Excuse me, sir. So we can form nitrogen from azides, but on a large scale, it is difficult. It is good. It is like a great reaction on a large
No,
scale.
we're not talking about the. Yeah. We're not even talking about large scale. I'm talking
Okay,
about even to make sufficient amounts for doing laboratory experiments.
sir. Thank you.
Certainly, on a large scale, it would not be practical, and you can imagine that when I can get it from N2 directly from the atmosphere, why would I do it? It wouldn't make much sense. But yes, in that time, maybe the azide was a possibility of getting a nitrogen from such a source, because after all, you are only doing lab experiments. Anything else? So this is the total process, which I have already explained to you. This is in a like a flow sheet. You can go through it, the process flow sheet. As I told you, I mean, the catalyst development was the other big thing that BASF did. And just as some of you said, drawing inspiration on the earlier work of Ramsay and Young. Okay. Now, the other thing is, what they did is, BASF, they were great at transferring knowledge from one application to another. Like, for example, you have seen in the contact process, how you carry out a reaction in multiple steps, where you let it go adiabatically and then you cool and then again let it go. And exactly the same kind of approach they took. They let it go adiabatically, then you cool it, again an adiabatic reaction, and slowly you kind of increase the conversion of the ammonia by this kind of a process. The other was, you see, because you could not get 100% conversion, unlike in the case of the in the contact process. The conversion was relatively more limited, something like 20-30%. So probably what they had to do was that they removed the ammonia, again just like the double contact, double absorption, where by removing the SO3, you can drive the equilibrium to the right. So they would have said, let's do the same thing. We'll separate out the ammonia, and then we will again maybe fill up with more nitrogen and hydrogen, and repressurize and keep going. Okay, so that's the way they would have done it. But tell me one thing. What would be the best way to take out ammonia from the product mixture? So what am I've got
Dissolving
nitrogen
it.
and hydrogen. I'm forming, yeah. What will I do?
Dissolving it.
Dissolving it. Okay. One possibility: dissolve.
Or sir, even cooling.
What is even what?
Cooling
What did you
down.
say? Cooling. Oh, nice. And why did you think about that?
So because ammonia is very far apart from a real gas, so it will condense down. Nitrogen and hydrogen won't condense down.
Oh, very nice. Very nice. That's exactly what is done today. There is one more thing which you did not mention. Can you integrate it with the process and see if there are any advantages of doing that?
It is high pressure, so it will be easier to
Yes.
compress.
Yes. Because ammonia very different from gases in terms of BP, boiling point, and because the reactants are under pressure, right? 200 bar pressure. And I was just trying to work out today. I just said, let me check what is the boiling point. The boiling point of ammonia is 132 degrees centigrade at 113 bar pressure. So if you're talking about 200 bar pressure, it would be still higher. And so you don't have to do a whole lot of cooling, okay, because your temperature is around, today you can do ammonia synthesis at about 350 degrees centigrade. You can see 300 what? Yeah. So around say 350, I can do reactions over here. So, I just have to do a marginal cooling, and I've got it in a liquefied form. And then I take it out as a liquid and recycle the gases. And, the other advantage compared to dissolving the ammonia in water, let's say, which is what, by the way, Haber was doing. The advantage is that the gas would become wet. And so again, I'll have to dry the gas. So that's another headache, drying again the gas. And also, in water, there will always be some oxygen. And so again, if some of these gases get introduced because of this, so you'd much rather avoid it. Okay, so cooling is the best option. Everybody agrees? All clear?
Yes, sir.
Okay. Now let's see another thing, a few things from the more from the chemical engineering angle. Let's see some of the parameters, operating parameters. Yeah, you can see that temperature 360 to 520 degrees centigrade. Now this is very interesting. You see, what is happening is we know that there are multiple beds. You have seen that you don't have to have necessarily one bed of catalyst. Like in the other case, in the contact process, we have seen there are 4 beds of catalyst. So it could be that your initial reactions you would do at a higher temperature so that you are speeding up the entire process. And as you are achieving or striving and moving towards the equilibrium position, you'll start reducing your temperature because lower temperatures naturally favor the conversion. So you may actually do that. And there are now catalysts that have been invented where you can do low temperature ammonia synthesis. One can reach today even 360 degrees centigrade. Now the pressure, typically, although such wide pressure ranges have been mentioned, and pressure is, of course, advantageous. If you have a higher pressure, naturally, 4 moles are going into 2 moles of ammonia. So obviously, at higher pressure, the equilibrium will be favorable. But getting equipment at that kind of a pressure is not so easy. So usually people will probably compromise and work at a pressure of around 200 to 250 bar. Now, this is another very interesting thing, the space velocity, which is effectively how many bed, suppose my bed volume of catalyst is 1 liter. Okay. So my space velocity, if it is 1000, means I am passing 1000 liters of the reactant mixture per hour through this catalyst bed, and your reaction has to happen in that time. So you can imagine how efficient it has got to be, and this is the kind of space velocities that they keep. Otherwise, you cannot get these kinds of huge, massive quantities of ammonia being produced from these plants. It's only because of the kinetics also being extremely fast for these processes. There are also poisons that you need to be aware of, and oxygen and oxygen compounds are poisons. So you need to be careful. You can see normally these have to be kept to less than 3 ppm. So process control is another very crucial thing. That means you have to be able to analyze things at that kind of concentrations. You have studied water and dissolved oxygen, so you've got some idea, how to estimate oxygen. The other is, from this data, you will be able to see that this is relative activity versus particle diameter. So if I reduce my particle size, as you would expect, your activity would, if I go here, let's say, my activity can be much higher. So you can see how with reduced particle size, my activity is going up. So what people will try to do is to make a very fine catalyst and then to pelletize this kind of a fine catalyst so that they still retain the high surface area. And at the same time, they will do it in a way that they are minimizing the pressure drop, even though my catalyst particles are so small. That's where all the engineering comes in. What kind of forms of these catalysts, etc., will give you these kinds of favorable effects? Those are the kinds of things that many people in the area of material science they work on. The other, as we had learned, is that if you want a good heat recovery, because it's a reaction, so you want to obviously extract the heat. We know that if you do it isothermally, you can never extract heat. I mean, in an efficient manner, because the temperatures are so low. But when you do it adiabatically, obviously I can extract good quality heat. Second, what is the heat being formed from? Reaction, right? It's an exothermic reaction, and that is the reaction which is generating heat. So the more reaction I have, the more will be the heat that is generated, and the better will be the quality of the heat that I extract. So, the rate of the reaction also favors better heat recovery from the system. The biggest challenge in all of these processes is the poisoning of the catalyst or the deactivation of the catalyst. Because you're operating at a fairly high temperature and you're wanting to work at very fine particle size, these particles might start sintering at those temperatures, and therefore I lose surface area. When I lose surface area, I lose catalytic activity. So that's a problem. Even a clean gas means without any impurities, even that will lose activity because of sintering. Not to speak of what will happen if I have got contamination in my gas. So if I've got contaminants like CO, CO2, etc., one is that they can poison the catalyst, and also these things can sometimes induce sintering. So sintering may happen not only because of temperature, but because of the presence of impurities in your reaction mixture. So these are all the things that one has to look out for while carrying out this process.
I've tried to put 18 of the highest volume chemicals that are made in the world. So ethylene, methanol, propylene, benzene, toluene, xylene, etc. What you can see is that ammonia actually releases the highest amount of greenhouse gases. Okay, the ammonia process, well, that is for two reasons. One is the production of ammonia is a very high volume production. And the second is, even with all the energy efficiencies, etc., it is quite an energy guzzler. The Haber process, the Haber-Bosch process, it could have been much worse, but for the fact that CO2 is actually consumed for urea manufacture. So anyone who can make a dent over there, it will be fantastic. Now, so you had CO2 as the co-product from this whole process, and it is not that these people were the inventors of urea. As you know, from the days of Wohler, urea had been already made, and people also knew that urea is a fantastic fertilizer for plants as a nitrogen source. The great thing was that Bosch was able to link up this whole thing, and he came up with a somewhat modified kind of a process, which is also known as the Bosch urea process. In the first step, what you do is you take ammonia, carbon dioxide, and ammonia has been produced, CO2 as byproduct, and you form ammonium carbamate. And then in a second step, the ammonium carbamate, if you heat, it gets converted into urea and water. The reason why you need to do it in two steps is that their thermodynamic requirements are very different for the two steps. In the first step, you can, this one, actually it's got a fairly negative enthalpy. So you need to operate it at a different temperature domain. You understand? And then once I have isolated the carbamate, free of all of this, then I heat it, just like we took sodium bicarbonate and converted it into sodium carbonate. Almost in the same way, and I end up making urea and water. Now, again, very, very tricky. It looks so simple, but what happens is that there is a parallel reaction. If you're not careful, that can happen, which is urea can react with itself and form what is known as biurate, okay, with the release of 1 mole of ammonia. Now, urea is a fantastic fertilizer. Biurate is terrible for the plants. It can cause what is known as leaf burning. And the second is that it's also not too difficult to have the reverse reaction, which is urea getting hydrolyzed to form ammonia and CO2. So you have to control the process in a way that these side products are kept to the barest minimum. We'll discuss the oxidation of ammonia to nitric acid because that again is a very important component in fertilizers. Okay, and that's one of the biggest applications of nitric acid, and the other being, of course, in ammunition, in explosives. Now, what you will see is that when earlier people it's not as if people were not making nitric acid, but they were making it from some kind of a nitrate source. There were some natural sources of nitrate which were available, but it was very clear that those are all going to deplete and there'll be nothing left. So it is something like the way you have a situation with fossil fuel today, that you don't know how long it will last. So there was a problem with nitrates at that time. Nitric acid, as you know, is very important for explosives, ammunition, dye stuff. And today, the most important application is in fertilizer. That's the biggest application. Now, in fact, it's ironic, but before, as we discussed, that when Haber process started, they were really not looking at trying to make ammonia. What they were trying to do was activate nitrogen and form oxides of nitrogen, but that turned out to be very inefficient. And then probably one would have thought that, okay, maybe at least they can be used for making nitrates, but that also didn't turn out to be quite so correct. And ultimately, the irony is that nitric acid is actually produced from ammonia. It's not the other way around, that you first make some nitrate salts and then make ammonia. It's the reverse. Nitric acid is made from ammonia. And if you look at the consumption in the world, not as big as sulfuric acid, but still quite big, quite large. It's about 60 million tons. Now, this is again a very classic process. In some ways, you will see it as a replica of the contact process, but in other ways, I will say it is a more challenging process than the contact process. Contact process relatively is easier than this. Can anyone tell me why that might be the case? Why is the contact process relatively easier than the nitric acid process? I mean, of course, I have not even discussed the process with you. Well, one reason, of course, is that, nitric acid is much more explosive. So you need to be very careful about it. And what you'll find is that there are many more competing reactions which are possible in the case of nitric acid, which wasn't the case with, let's say, converting SO2 to SO3. Either you got SO3 or it remained as SO2, but there wasn't anything else. But here you will find that there are other competing reactions which make it very difficult. The second is that over here you go through a two-step process of ultimately trying to make nitrogen dioxide, but that is not made directly. One first makes N oxide, and then N oxide is converted very easily through a non-catalytic process into NO2, and that then ultimately gives us nitric acid. And we will discuss this in a bit more detail along with the thermodynamics. If you look at this reaction, which is the first step, that is converting ammonia into N oxide. Now, I think you need to understand that there was no other choice. The only synthetic product which had become available was ammonia. There was nothing else. So it looked logical to look at the oxidation of ammonia to nitric acid. And if you see the stoichiometry, you have got 9 moles on the left, and you've got 10 moles here, which means that lower pressures should actually be used. But you'll also find that that's not quite what is done, right? And it's highly exothermic, as you can see. What you would thermodynamically expect is that low temperature and low pressure would both favor the reaction. But that's not quite what is done. So let us now try and understand the complexities of this process as, let's say, compared to the contact process. Well, along with this, there are two side reactions which can take place. In fact, there's another side reaction involving the product NO, which I'll talk about later on. But one of them is ammonia reacting with oxygen and forming nitrogen molecule. So it's like just going back to the element. Ammonia reacting with oxygen and forming nitrous oxide, N2O. Both of these are like dead ends. Once you have formed those, then you cannot again convert those into NO. So it would be disastrous if, for example, these were to occur. Now, thermodynamically, if you look at it, this has actually got a even higher negative enthalpy, minus 1267 kilojoule per mole compared to that. And effectively what that means is that you would possibly think that this will be favored. So this is where kinetics comes in. What we are discussing is the thermodynamic aspect. Now, kinetically, what people found is that the lower the temperature, the more is the predominance of this reaction, and the higher the temperature, basically you can actually get a reasonably good selectivity for formation of this. Even though, for example, this is thermodynamically more favored, but the rate of reaction, the differential rate of reaction is much higher for this as you raise the temperature. The second very important point to note is that we said, and you can see that higher pressures will not favor this reaction. And so you should keep your pressure low. But then what happens is that when you have a continuous process and once you form the NO, you don't want the NO to do any useless reaction. So what you want to do is you want to minimize the contact time of the product NO with the catalyst. The only way to do that, and literally that time is of the order of millisecond and sub-millisecond. That's the kind of time that it sees the catalyst. Whatever has to happen will happen in that time. So what happens is that that kind of a very high space velocity, then what will be required is that you have to have a high initial pressure, which will then ensure that you're having a very rapid flow of the feed through the catalyst. Reacts and off it goes. There is no time given for it. Because of that, what happens is that in reality, one does the reaction at about 820 to 923 degrees, even though, we saw in the contact process that it plays havoc. Here also, you may not get more than, maybe 10-15% in a single pass. But that's all right. At least what you will not do is that you will not form side products. And the second is, again, unfavorable from the thermodynamics point of view. You do it at higher pressure. Although over here it's written 11, it could be anywhere from 4 bar to 11 bar. So if you therefore were to look at what are the important temperature considerations, one might say that even though higher yields would be obtained at lower temperatures, the forward reaction is exothermic. The process is carried out at high temperatures. This is because the rate at which the reaction proceeds at low temperatures, that's the other reason. The rate of the reaction, the favored reaction, is too low at low temperatures. So you want to make sure that it actually reacts much faster. And to compensate for the resultant loss in product yield, the gas mixture is passed over a catalyst a number of times to produce a moderate yield of NO. So it's not one pass. You pass it through, again it repeats. And that's how you build up the concentration of NO. And that has been found to be the best way to avoid all the side reactions. And this is the other critical thing, the reason why, on the one hand, you need a high temperature because the rate is too low at lower temperature, and as I told you, those other reactions will catch up on you. The second reason is because NO at high temperatures can decompose to nitrogen and oxygen. You don't want that. So even before it has a chance to do that, off it goes from the catalyst. Is that clear? And so there are these nuances, and in that sense it is a far more complex process than the contact process. But the interesting thing is that this process too was developed at BASF. So all the learning which BASF had in all their processes were very nicely utilized in this. Okay, this process also is you must know was invented by a very famous man, Ostwald, and it's actually the Ostwald process. Now, the other thing you can see, to avoid that reaction, okay, the side reaction, the gas mixture is passed across the catalyst very rapidly, something like 3 milliseconds. That's the kind of time. And to achieve this high flow rate, the reaction is performed at high pressures. Even the lower pressures would result in a higher product yield. This is what engineering is all about. You know, you as engineers, you'll have to look at trade-offs. There will be some things which will be good, some things which will not be good, and how to make those compromises is really what the challenge is. I mean, as good chemical engineers, it is that aspect that you will need to look at. There is no ideal situation. So the consequential loss in yield of NO is compensated for by the increased reaction rates and the quality of product obtained. So as you go to higher temperatures, you have a very high reaction rate, but on the other hand, you have a high pressure, so it doesn't allow this reaction to proceed. And so you get a reasonably good rate. Along with the many passes, you get a reasonably good conversion, and the side products are kept to a bare minimum, as you will see. Okay, now this requires a very expensive catalyst. The catalyst that does the job is really platinum. What you can see is that the efficiency of the reaction peaks around 800 degrees, and the other thing that you will see is that if you carry it out at two different pressures, 100 kilopascal, which is basically 1 bar and 4 bar sort of a pressure, what you will see is that obviously the lower pressures will give you a higher efficiency, but that's not what you do, as we discussed. You do it at a higher pressure. We discussed some very fortuitous things when we discussed about the vanadium pentoxide catalyst, and we said it was almost made for the contact process. What were those fortuitous things and great things that we found in the vanadium pentoxide catalyst? What did we find? Things which were fit in very well with the contact process? Yeah. Leave aside the cost, that's good. But anything else from the technical merits? Poisoning. Okay. That's also very important. Anything else? Oxygen. Yeah. I mean, that was actually slightly inferior to platinum. Yeah. Excellent. Excellent. Okay. So you have, we know that the ideal reaction temperature in terms of conversion was around 400 degrees centigrade. And we also knew that by the time you go to about 600-700 degrees centigrade, the conversion basically drops off to close to zero. So the window was 400 to 600 degrees centigrade, thereabouts. Now, what did we find? Vanadium pentoxide melts at 400 degrees, right? And so we could do it as in a liquid state of the catalyst, which meant that my activity of the catalyst was much higher, because now I'm not only talking about surface area, I'm talking about the bulk of the catalyst being useful for the reaction. The second is it volatilized around 6 50 or thereabouts, but I didn't need to because I wanted to confine the temperature to around 600. So it had a perfect match in terms of its melting and boiling points, almost in tandem with the kind of plot that you saw for conversion versus temperature. Now here again, something very similar you will notice, something very fortuitous. Now there was no way in the world they would be able to practice this invention if there was any significant loss of platinum. If platinum just disappears, then there's a problem. Now what they found is that if they make an alloy of platinum with rhodium, rhodium is again also a very costly metal. What they found is that if you have about 10% of rhodium, they get the maximum efficiency of conversion. So it was good to have rhodium, along with the platinum. You can see from less than 96 and it peaked over here and then it decayed. But the other great thing that happened when they put rhodium was that they found without the use of rhodium, there was a fair amount of loss of platinum. And the moment they put the rhodium, they found that the loss of platinum is subsiding. And obviously it's the property of the alloy of platinum and rhodium which behave differently. The interesting thing is that the point at which it virtually becomes like a horizontal line, and so there's not much more to be gained, is again around here. So there was substantial loss of platinum, it tapered off and became very low at a point like this, and this also happened to be the point at which you got maximum efficiency. So it was wonderful, and again, like the vanadium pentoxide, a great example of multiple gains accruing from one common thing. And this is really all about innovation and cleverness that they were able to find this. I hope you also understand that when you are doing industrial engineering, that it is not about whether I get 60% yield and 90% yield. It's about the difference between 96% and 98%. Okay, and you can see all this work is really struggling in a very narrow range. But that is critical. That is the difference between a process not being viable and a process being viable. So please remember that as far as industrial engineering is concerned.
I must tell you, you all answered splendidly today.
Thank you, sir.
Thank you, sir.